All right, so get this. We're diving into computer memory, but not the kind you're used to.
Okay.
We're talking way beyond that.
Right.
Think RAM CDs, even Blu-ray discs.
Yeah, those are pretty standard.
Exactly. But here's the thing. All these technologies, they're power hungry.
Uh-huh.
Especially when you're trying to save data.
I see where you're going with this.
So what if there was a way to make that whole process like way more efficient?
Well, yeah, that'd be incredible, especially with how much data we're all using these days.
It'd be a game changer, right?
Yeah.
And guess what? Scientists may have actually found a way.
Really?
Yeah, they've discovered this material that can transform from a crystal to a glass and get this using 1 billion times less energy.
1 billion times less.
You heard that right? 1 billion?
That's mind-blowing.
It's absolutely wild, right?
Yeah. So what is this miracle material?
It's called indium selenide.
Indium selenide.
Yeah, and it's what's known as a ferroelectric material.
Okay, so that means?
Basically, it just means it has these special properties that make this whole discovery possible.
Interesting.
But before we get too deep into how it all works, let's take a step back.
Okay, sure.
And talk about the current process, the way we do things now.
Right.
So right now, to create the glass state for memory storage, we use this method called melt quench.
Melt quench?
Yeah, and it's basically as energy intensive as it sounds.
Oh, I bet.
Imagine like heating something up to over 800 degrees Celsius.
800 degrees?
Yeah, that's hotter than a pizza oven.
Wow.
And then you take that and you instantly cool it down.
So like taking molten lava and dunking it in an ice bath.
It's pretty much exactly like that.
I can see why that would be a problem.
Right, and that's a big part of the reason why like your laptop gets all heated up when you're working on a big project, or your phone battery just drains when you're recording a video.
Yeah, that makes sense.
So now let's talk about how this new method is different.
Okay, yeah, the 1 billion times less energy thing.
Right. So instead of all that crazy heat, the researchers, they found that by just passing an electric current through the indium selenide, it transforms into glass.
Without melting it.
Exactly.
How is that even possible?
That's the million-dollar question, isn't it?
Yeah.
Would you believe me if I told you it all comes down to tiny little earthquakes?
Earthquakes.
Tiny ones. Like at the atomic level.
Okay, now I'm really intrigued.
So picture this. You've got the indium selenide, and it's kind of like a neatly stacked deck of cards.
Right, I'm visualizing it.
Now, when you pass an electric current through it, those cards, the layers of the material, they start to slide against each other. And as they shift, they form these tiny little regions or domains.
Domains.
Yeah, and these domains, they have opposite electrical charges.
So it's like creating these tiny little electrical magnets within the material.
You got it. And now imagine those domains are like tectonic plates bumping and grinding against each other.
Okay, I'm following.
And all that bumping and grinding, it creates these tiny little earthquakes within the material. Whoa. And those shocks, that's what causes the crystal to actually transform into a glassy state.
So instead of blasting it with heat, we're essentially tickling the atoms into rearranging themselves.
That's a great way to put it. Yeah. And it all comes down to these unique properties of indium selenide.
Like what?
Well, its 2D structure, it's ferroelectricity, and it's piezoelectricity.
Okay, so those are like the secret ingredients that make this ultra-low energy transformation possible.
Precisely.
That's incredible. I mean, it's amazing to think that just a tiny little tweak at the atomic level can have such a huge impact on a material's properties.
Right. And this discovery, it's like opening up this whole new world of possibilities.
Not just for memory storage, but for
pretty much everything.
Exactly.
Okay, so now that we've got a good grasp on how this amazing material works,
yeah,
let's take a look at what those possibilities might actually be.
definitely. I'm ready to dive deeper.
All right, we'll do just that in part 2 of our deep dive.
Sounds good.
But before we get ahead of ourselves, I want to let all this sink in for a minute.
Yeah, no, it's definitely a lot to process.
I mean, we're talking about a completely new way of manipulating materials.
Right.
A way that could totally revolutionize the way we live and interact with the world around us.
It's almost like we've stumbled upon a secret passage.
To a world we never knew existed.
Exactly.
All right, so let's take a break and we'll come back and explore that new world together in part 2.
I can't wait. It's wild when you think about it. Like, we could potentially have data centers that are way more efficient and have a much smaller carbon footprint.
Okay, so that's faster downloads and greener data centers.
Exactly.
That's huge. But what about other applications? I feel like we've only just scratched the surface here.
Oh, you're absolutely right. The potential goes way beyond just memory storage.
Like what else?
Well, for instance, imagine electric vehicles that can charge super fast and have batteries that last way longer.
No more range anxiety or waiting around at those charging stations for hours.
Exactly.
That would be a game changer.
And that's just one example. Think about all the medical devices out there.
Pacemakers, insulin pumps.
Yeah, all of those. They rely on efficient energy storage.
So this technology could lead to like smaller, more powerful devices.
And ones that don't need to be charged as often.
That would be huge for so many people.
It really would.
It's pretty amazing to think that something discovered in a materials science lab could have such a massive impact on healthcare.
Yeah. It just goes to show you how interconnected all these different scientific disciplines are.
And how important basic research is.
Absolutely. But, we've got to be realistic, too.
What do you mean?
Well, there are some challenges. Indium selenide is actually a pretty rare material.
So it's like we have this amazing recipe, but we're missing one of the key ingredients.
Yeah, kind of. Scaling up production to actually meet global demand could be tricky.
So what can we do about that?
Well, researchers are already looking into ways to either synthesize indium selenide more efficiently or find other materials that have similar properties.
So it's like a relay race where different teams have to work together to reach the finish line.
That's a great analogy. And the success of this technology really depends on everyone playing their part.
It's exciting to think about all the different fields that could be impacted by this.
I know, right? It's like a ripple effect spreading outwards, changing everything it touches.
It feels like we're on the cusp of something truly transformative.
Like we found a key that unlocks a door to a whole new world.
Exactly.
A world of possibilities.
It's easy to get caught up in all the excitement about these potential applications.
For sure.
But we got to remember, this is still early stage research.
Absolutely. There's a lot more work to be done before we actually see these technologies being used everywhere.
But even so, the initial results are super promising.
They really are.
Before we wrap up this part, I want to leave our listeners with this thought. What if we could take this a step further? What if we could use this knowledge to not just change existing materials, but to design entirely new ones from scratch?
That's a pretty mind-blowing concept.
We'll explore that idea in part 3 of our deep dive. So we've been talking about indium selenide and how it could revolutionize memory technology.
Yeah, it's pretty amazing stuff.
But what if this is just the tip of the iceberg? What if this discovery opens up this whole new world of material design?
So that's a really interesting thought. We've seen how manipulating materials at the atomic level can lead to some pretty incredible breakthroughs.
Right.
But actually designing new materials from scratch, that's a whole other challenge.
It's like going from baking a cake to inventing a whole new type of flour.
Yeah, that's a good way to put it. What kind of properties could we create if we had that level of control over matter?
It's mind-blowing to think about.
I know. Imagine materials that are stronger than steel but lighter than a feather.
Wow.
Or fabrics that can change color whenever you want.
That'd be so cool.
Or even self-healing structures that can repair themselves just like living tissue.
Self-healing structures. That sounds like something straight out of science fiction.
I know, right? But the potential is there. If we can really understand and control the forces that govern how atoms interact, we could theoretically design materials with any properties we want.
So instead of just finding materials that nature provides,
we could actually become architects of matter.
Creating materials that have never even existed before.
Exactly. It would be a total paradigm shift in materials science.
This is blowing my mind.
Yeah.
It's like we're about to unlock this secret code that governs the building blocks of the universe.
It is pretty exciting, but it's also a bit daunting.
How so?
Well, for one thing, manipulating matter at the atomic level requires an insane amount of precision and control.
Yeah, I can imagine.
We're talking about manipulating individual atoms and molecules.
So it's kind of like trying to build a house of cards, but with atoms instead of cards.
Pretty much. It takes an incredibly steady hand and a really deep understanding of all the forces at play.
So this isn't something that's going to happen overnight.
No, definitely not. It'll probably take years, if not decades, of research and development before we can really design materials from scratch as easily as we design buildings or machines.
But even if it takes a while, the potential rewards seem worth it.
Oh, absolutely. Just imagine the possibilities. We could create materials that are perfectly tailored for any application.
Like super efficient solar panels that capture almost all of the sun's energy.
Or ultra-strong lightweight materials that could revolutionize transportation and construction.
It's like we're standing at the very beginning of a new era in material science.
An era where the only limit is our imagination.
Well said. Well, I think it's time to wrap up our deep dive into the world of shockingly efficient memory tech and all the amazing possibilities it has unlocked.
It's been a fascinating journey exploring this new material, indium selenide, and how it could revolutionize memory storage.
We've covered a lot of ground today.
From the energy-saving potential of this technology to the implications it could have on everything from our electronics to healthcare to transportation.
Even to the way we design and build the world around us.
And hopefully we've given you a sense of wonder and excitement about the future of materials science.
To all our listeners out there, thanks for joining us on this incredible journey. We hope you found it as mind-expanding and inspiring as we did.
And remember, keep exploring, keep learning, and never stop asking questions.
Until next time.